Since we're adding many things together, we can use sigma notation to simplify our formulas. So before we had, in the last section, r sub n is equal to the adding up of all the rectangles. We can now use sigma notation. This is the notation here, and I'll describe it in more detail in a second. But the formula is r sub n is equal to delta x times the sigma notation j equals 1 to n of a function. So this symbol here is sigma, and the way that it works is sigma means add up, and this lower limit and on the top there'll be an upper limit are very important. And basically what happens is your function that you are applying your sigma to starts with j equals 1, so you find f of 1, and then you add, sigma means add, f of 2. You use the next integer up from 1, so you use f of 2, and then you use the next integer up, f of 3, and you continue that process until you get to your upper bound, in this case n. And that's exactly what we did last time, but our n was 4. We had 1, 2, 3, and 4 being subbed in. This formula over here can also be found, a similar sigma notation formula can be found for the left limits, and that would be delta x times the sigma notation from j equals 0 to n minus 1, because you're using left endpoints. You have slightly different variables there, and then your function notation is still the same, and there is a midpoint one as well. Midpoint notation, and j equals 1 to n times the delta x and the sigma notation of, and this is a little bit more complicated because you are using midpoint, and so a plus j minus 1/2 times delta x. So let's take a look at the last example that we did, but now we're going to use this formula. So our n is still 4. You get that from the subscript on the r sub n, and our delta x is still b minus a over n, and our b is 4 still, minus 0 and 4 subintervals, so 1, as we saw in the last example. So now we substitute that information in, so delta x is 1, our j goes from 1 to 4 now, and our a value is 0, as you can see in the interval, and our j value is still j, and delta x, as we said, calculated it out to be 1. And so simplifying some of the algebra in that function notation part, it's still sigma notation of j equals 1 to 4, and 0 plus j times 1 is j, and in front that 1 is still a 1. Now I substitute j as 1 into my function, so I'm substituting in for f of 1, f of 2, f of 3. I keep doing that till I get to that top bound, which is f of 4. And we did this before, so the function is f of x equals x cubed, so I get 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, which is 100. Notice that that function notation, sigma notation, is just a fast way of adding up a bunch of numbers. And also notice that the more subintervals we have, the better off the result is for our area A. And we saw that with technology as we increased A, we got better and better, increased n, we got better and better results for A. And if we can take n to infinity, we would have A exactly. And we can take n to infinity, we just have to use limits. And the limit as n goes to infinity of r sub n or l sub n or m sub n will be A. We'll exactly calculate the area underneath the graph. So here's an example. Find the area under the graph of this function on the closed interval 1, 2. So the area is the limit as n goes to infinity of r sub n. Divide r sub n up into infinite number of little tiny rectangles. And again, we have to calculate our delta x. And in this case, the delta x is equal to, again, b minus a over n, so 2 minus 1 over n. I don't know my n value, so I just simplify that to 1 over n. And so r sub n now equals, I use the formula, delta x times j equals 1 to n of f of a plus j times delta x. And substitute in what I know. So 1 over n is my delta x, my sigma notation, j equals 1 going to n will eventually go to infinity. And my a value on this interval is 1, and j times delta x is j times 1 over n. Now f of x is x squared minus x plus 5, and I want to know what f of 1 plus j over n is, so that I can substitute it in for 1 plus j over n in my sigma notation formula. So it's 1 plus j over n squared minus 1 plus j over n plus 5, and simplifying that magically gives me j squared over n squared plus j over n plus 5. So I substitute that in for this part, and I've just rewritten the question using the substitution. Now, sigma notation works a lot like the integrals do, where you can actually factor out constants, you can factor out numbers, and you can apply the sigma notation to each part of the question. So I can apply the sigma notation to each part, and then I can factor out, or I can think about simplifying out each of these constant terms. J is changing, but the n value, it'll go to infinity, but it isn't changing, so we consider that a constant. So simplifying that out and distributing the 1 over n to all three terms gives me 1 over n cubed as the j squared comes out. And for the next term, 1 over n squared times the sigma notation of j plus 1 over n. There's that distribution I'm doing. It's actually 5 times 5 over n times the sigma notation of j equals 1 to n of just the number 1. And to simplify these parts, I do need to know a little bit more math. It's going to require us to know something about sigma notation called the power sum rules. So let's list those out. The power sum rules. So there's one for j equals 1 to n of 1. It's just equal to n every time. If you have j equals 1 to n of j squared, it's a bit more complicated. J equals 1 to n, j equals 1 to n of j is a bit more complicated. J squared is even more complicated. And the sigma notation of j equals 1 to n of j cubed is equal to n to the 4th over 4 plus n cubed over 2 plus n squared over 4. So we need some of these, namely these three, to help us with the sigma notation from the question that we were just doing. So here's the question we were just doing. I have a j squared term, sigma notation, so I have a simplification for that. You do not need to know how to derive these power sum rules, but you do need to know how to use them. And here are the simplifications for each one. Giving myself a little bit more room, I now multiply the 1 over n cubed through, giving me 1/3 plus 1 over n squared plus 1 over 6n squared, 1 over 2n, plus 1 over 6n squared plus 1/2 plus 1 over 2n plus 5, which gives me 35 over 6 plus 1 over n plus 1 over 6n squared. And now I actually want to go back to the very beginning and calculate the area. And the area requires me to take the r sub n and apply limit as n goes to infinity. So there's my r sub n formula. Now I apply the limit as n goes to infinity to this formula that I've generated, and you'll see that the last two terms go to 0. So that leaves me with 35 over 6, which is approximately equal to 5.83. It's actually 5.83 repeating. You can check this with technology if you'd like, but it is correct. Enjoy the homework.